So you noticed we have put 1-5 into many pieces, because 1-5 to me is one of the most important lessons in chapter 1, because it's taking functions and kind of moving them around and manipulating them. And then the last part of it, 1-5D, is about graphing piecewise functions. A lot of students like to make graphing a piecewise function a lot harder than you need to, okay? So I want to take you through the kind of steps of a best practice of how to graph a piecewise function. So what is a piecewise function? It's a function that breaks into multiple pieces based on the domain. So many times you will see like a bracket like we see in our function that we see down here, okay? So it says to graph the piecewise function. So what we want to do is we want to first look at our borders. See those borders there? So we have something that switches at -4, between -4 and 2, and then at 2 again. So the first thing when we go to graph these, my suggestion would be at -4, put a little dashed line. At +2, put a little dashed line. Those are our borders. Okay? Now you want to think of them somewhat as the border of a country. We do not have privileges in the other country, so we only can graph the piece of the function that lives in that border, okay? So first, what I would like to do is I would like to graph this top one. Now, you might recall from what we know about our parent function that our parent function is a v. Okay? What this divided by 2 is, it just is going to take our v and it's going to kind of squish it down a little bit. And you'll notice that our v, we only need the portion to the left of -4. So if we think about our v is going to look kind of like this. So we're really only going to see a little portion of the v. Now let me show you how to do it. Because -4 is on our border, I definitely want to see what -4 is doing. And then anything less than -4, why don't we plug in -5 and -6? Now we know it's a v, but we only get to show up in that portion of our border. So at -4, the absolute value of -4 is 4. 4 divided by 2 is 2, so that's a 2. -5, the absolute value of that is 5, divided by 2 is 2.5. Now you can write 5/2, there's nothing wrong with that, but because we're graphing, that decimal value is a little more helpful. The absolute value of -6 is 6, 6 divided by 2 is 3. Now, it's very important that you note that we are allowed to equal that value for that portion of the graph. So over here at -4, we are at a height of 2, and we are allowed to be there, so I make a dot. And then at -5, we're at 2.5, and at -6, we're at 3. So only this part of our v is allowed. The other part of our v, it's kind of like it's invisible. So the other part of our v is right here. But we don't see it because we only get the portion that lives in the part of the country it's allowed to live in. Okay? Now let's look at this one. A negative on the inside of the function flips it across the y-axis. So that's what this negative does. So normally our square root looks kind of like that, but that negative inside, we learned, flips it over here. Okay? Now, if it flips it over here, we are only going to show up between -4 and 2. So just like we're going to have like a little part of that showing and then nothing else. So let's draw that. So what would I plug in there? Well, I'd plug in 0. I would plug in -1, and I would plug in -4 because that's a border value anyway. Okay. So if I plug into this, the opposite of 0 is 0. The square root of that is 0. The opposite of -1 is 1. The square root of that is 1. The opposite of -4 is 4. The square root of that is 2. So technically, we would have an open circle here, but it's already been colored in, so we really don't have to worry about that. The other one colored in and matched up perfectly. But at -1, we're at 1, and at 0, we're at 0. So there's just a little chunk of a graph right there. Is everything working on your devices?
Yes.
Okay. Now we're going to plug into the absolute value of x minus 2, another v. Anybody remember what happens when we subtract something on the inside of the function? Does it move left, right, up, or down? When we subtract on the inside of the function, does it move left, right, up, or down? Anything on the inside of the function goes the opposite way of what you expect. What you can think about is that x minus 2 equals 0 at 2. So the vertex of the v is at 2. So for this one, normally I would plug in 2, 3, and 1. But see how we only are allowed to plug in things bigger than 2. So this one's out. I can't plug in 1 because my v, so my v only lives in the area that's greater than or equal to 2. So I can only plug in things that are greater than or equal to 2. And so plugging in 2 is good, plugging in 3 is good. If you wanted another value, you could plug in 4, it doesn't matter. If we plug in 2, we get 0. If we plug in 3, we get the absolute value of 1, which is 1. So it's allowed to stand on that border. And it's the right side of the v. Because the other side is not allowed to be there, or it will be rounded up by Border Patrol. I don't know, but it's not allowed to live there, okay? So it's, so the graphs will look a little wonky because sometimes you only see a portion of that graph because the borders take over and then you just stop it. So even though this one's a V, we don't see much of our V at all. This one's a V, we don't see much of our V at all. This one is a swoop to the left and we don't see much of that either. The borders truncate or stop the graph. So that's why I always put my borders on first, so that when it's time to actually graph it, then I know where things start and stop again. That makes sense? Okay. So that one's pretty hard. So if you understood where that one came from, that's a good step. But I want to do another one as well, okay? And everybody have that one down. Okay, so our border is only 1. We have a weird one happening with this one, okay? So let's just put a border line here of 1. Now, when it says equal to 1 at this point, it is only a point. If I plug in 1, I get out 1 minus 1, which is 0 to the 4th, or 0. So that we can put on real quickly. At 1, I should be at a height of 0. So that's just a weird spot where if it just says, if x is equal to 1, plug it in here, what do you get? I get 0, and that's it, okay? This one here is going to be a part of a V of some sort, because it's an absolute value. It's going to be a v actually that moves to the right 3. This is a square root. This square root will head to the right. The 4 on the inside will actually just slightly stretch it a little bit, but I'll show you how to take care of that. So the first thing I always do is kind of look at, well, what do these pictures look like? Well, this is a V. This is a swoop to the right. This is just a point, so I don't really have to care about what the graph looks like. Okay, so let's do the V on the top there. The V on the top is for values less than 1. Now, normally it's a V that has scooched over to the right 3 and looks like this. But we can only use the V that is less than 1. So even though we're not allowed to plug in 1, I need kind of a spot to put an open circle. So I would put in 1, anything to left of 1, less than 1, like 0 and maybe -1. If you plug in 1, you get the absolute value of -2, which is 2. If you plug in 0, you get the absolute value of -3, which is 3. If you plug in -1, you get the absolute value of -4, which is 4. Okay. So what we're finding is just one arm of the V, and that's very common when you stop the V. You can't make the entire V. Okay. So at 1, we're at 2. This has to be an open circle because this does not include the equal to. So it's not allowed to equal 1. So at 1, we have an open circle at 2. At 0, that's just a nice point. At -1, that's just a nice point. So that it's just part of our V, not the whole thing. Okay. So that's just the left-hand arm of our V. So many times you just kind of get a little piece. Okay. Now let's talk about the square root of 4x. Now normally I would find the starting place of my square root. I know that this is going to start at 0 and swoop over, but let's figure out where it's going. I can only plug in points greater than 1, but I need to see what 1 gives me. Okay. If you plug in 1, you get the square root of 4, which is 2, but it has to be open again. Remember open when we were doing the interval notation, open circle didn't include the equal to, that's why. Okay. So at 1, we have an open circle at 2 again. Now there was already 1 there, but just to make it clear for you. Now where will 4x equal 9? That's gross. Let's go 16. 4x equals 16 at 4. So I'm just thinking, what's a nice square root? So 4 gives me a nice square root. The square root of 16 is 4. So at 4, I'm up at 4. So it's just that part of that swoop to the right. It should have been started here, but we have to chop it off because it's not allowed to go across the border. And so we stop it right there instead. Okay. Now you can plug in many points for square roots. I always ask myself, well, when is it going to equal 1? When is it going to equal 4? When is it going to equal 9? When is it going to equal 16? I try to plug in perfect numbers so that I get nice points. Okay. Any questions there? Okay, now let's go the opposite way and let's write a rule for our function. So we're going to call this function f of x. There are 3 distinct pieces, okay? We have a border at -4. We have a border at 2. Let's put those borders on there. Okay. Now, for this piece right here, do you remember how to make a horizontal line, what the equation is for a horizontal line? No, not f of x equals a number. Yeah, so we'll get a sloping line for some version of f of x equals x. This is just, a horizontal piece is just f of x equals a number, whatever that number happens to be. In this case, we're at 2. Do you see we're at 2? And so for that piece is where x's are less than -4, our function always equals 2. It's constant. That's our constant function. It equals 2. Let's look at this piece. We know that middle piece is between an x value of -4 and an x value of 2. None of the borders are closed in dots, so that's why we use our little open circles. Now that's a line. And what is our y-intercept? What's this line's y-intercept? It's -2, right? What's the slope? Down 1 over 1. The slope is -1. So if we just think about the line, a slope of -1, a y-intercept of -2, that's how we find the equation for that chunk. Let's look at this piece. That again is a line. I don't see the y-intercept, so I would keep picturing if that line did hit the y-axis where. It would hit it at -6. The slope is up 1 over 1, +1. See, up 1 over 1, up 1 over 1. So it's 1x minus 6. And that is for all x values that are bigger than 2. Okay? So what a piecewise function has to include, where does this function live? How would I graph that function if it was just a normal good old function? Where does this function live? How would I make an equation for that? In this case, line. Where does this function live? How would I make an equation for that line? And sometimes you have to actually extend it out to make it work. But you can plug in points as well. Once you have your picture drawn, plug in, here I would plug in -5, I get 2. Here you could plug in -2, you get 0. Here you could plug in 4, you should get -2, which you do. So you can check your work by plugging in some points for that region, and then it should get you what you want. Okay? Does that make sense how we got that function to work? These are weird. These are very kind of not intuitive. They're hard.
Can you go back up for a second?
Yep. Which do you need to see?
Just the last one that we just.
Okay. Now, for the first time, your homework is right below it, and you can just write on there. You don't need your own paper. And we're going to do the first one and maybe the last one together, okay?
Wait, can we do it on paper?
For today, I want you to practice doing it on here. I know. It's going to be frustrating at first, but I want you to practice using it. Okay. So we'll do 1 and 5 together, okay? Let's do 1 to get started. So write your name down. Okay, let's take a look at number 1. Okay, so we've got 2 lines. What is the border line? 2, so let's put the 2 down. I always put my border first, just so then it kind of keeps me in check as to where things are at. This one is just a line with a slope of -2 and a y-intercept of -1. Remember, the coefficient on your x is your slope. The number you added or subtracted is your starting place, okay? So to make our line, we're going to start at -1. We're going to count down 2 over 1. And I go until I hit my border, and I look, am I allowed to stand on my border? It has the equal to, so I can. And then I make my line only in the region where we live. Okay, so that's that. Now this is a line with a slope of -1, with a y-intercept of 4. Is the y-intercept where we're allowed to graph? Is the y-intercept of 4 in a spot that we're allowed to have?
No.
No. So what I do for lines, as long as I have a starting place, I can just continue the slope from there. So my starting place is the border line. So what I like to do is plug in the border. I know I'm not allowed to stand in the border because I'll get shot or something, so don't do that. So if I plug in 2, I get -2 plus 4, which is 2. So we just put a little open circle. And then you're allowed to travel the slope of down 1 over 1, or you can plug in 3, because that's allowed. If you plug in 3, you get -3 plus 4, or 1. So you can travel the slope down 1 over 1, or you can plug in points. You can plug in points for any of these, but just note, you're only allowed to be in that certain region. Because normally, look, normally I would graph a line. I would start at -4. I would go down 1 over 1, down 1 over 1, down 1 over 1, and make my line. Now, what I've seen some people do is they make the line, and then they just kind of erase the portion where you're not allowed to be standing. So it's really up to you how you do it, because each, okay. So we're not going to do 2, but let's talk about it. You're going to have a horizontal piece, a line, okay? Horizontal piece, a line, a line. A line, a line. A line, a horizontal piece. Horizontal piece. Now, we need to do 4 and 5 because we haven't talked too much about fourths. Even-powered polynomials look like a parabola. Odd look like a cubic. So even though this is a 4th power, it's just going to look like a parabola, okay? What the 4 does is it just kind of deepens the well in the parabola and then pulls the arms up a little higher, but it looks like a parabola, okay? So let's do 4. So our border is at -2. This is a horizontal piece. So you just go to -6. I'm not allowed to equal the border. And I just go over to the left. That's it. So I love the horizontal pieces. They're great. Okay. Now, this is a parabola-ish that is moved to the left 1. Okay. So it's going to look like this. Normally, right? It's a parabola moved to the left. But it has to stop when it gets to the border. That's all. Its little arm got chopped off. Okay? It went to the border, it got in trouble. It got its arm chopped off. Okay. So for that one, I would plug in some points. It's allowed to equal the border. So I would probably plug in the border. I know its vertex is at -1, and then maybe one more. So then I can just get a sense of how the rounded V thing is looking like. If you plug in -1 or -2, you get -1 inside the parenthesis to the 4th power is 1. So we can put that point on there. If we plug in -1, we get 0. Anything to the 0 to any power is still 0. If you plug in 0, you get 1, and that's 1. So see how it looks like a parabola, just like I expected, okay? So just knowing what something looked like is helpful. Okay, let's do 5. This is our reciprocal function. Remember how our reciprocal function looks? It has those pieces. It has a asymptote. And this one will have gone to the right to 4. So it kind of makes sense that the border's at 4. So let's put our border down. That piece is to less than or equal to 4. So let's put its top little border on. And it just looks like one of these. It's just, remember those we did? It just looks like that. Now normally it would have a piece right here that matches it, but I don't live over there. I only live where I am less than or equal to 4. So that piece gets erased. We can't use it. We only use the piece on the left. This is just a horizontal piece at -4. So we have an open circle. This time our horizontal goes to the right. Okay. So you don't have too many more to go. So your goal is to get these turned in. And when it's time to turn them in, I'll show you how to get them from the tablet onto your Google Classroom, okay? So there you go.